Okay, so let's start. In the previous class, we were looking at sub-exponential distributions and their properties. Right? So remember, the general theme will always be to derive exponential tail bounds on certain random variables or functions of random variables. And so far, we've mainly been looking at either individual random variables or sums of random variables, or maybe linear combinations of random variables. Now, in many applications, this is good enough, and in fact, you'll be able to derive exponential type of tail bounds only if the corresponding random variables in question are either sub-exponential or sub-Gaussian. So it has to be either at least sub-exponential if you want to derive an exponential tail bound, because by definition, if you have an exponential tail bound on the random variable for all t greater than or equal to 0, then it must necessarily be sub-exponential. Right? So for general random variables, it is not possible to derive exponential tail bounds. Correct. But then again, sometimes it's easy to show that a certain random variable is sub-exponential. Sometimes it is not. So what do we do in those scenarios where the random variable itself is fairly complicated and we don't really know the exact distribution? Correct. So we saw some examples. For example, if the random variable is bounded, then irrespective of what the actual distribution is, we know that it is going to be a sub-Gaussian distribution. Now we may not get the best possible constant, right? Because for example, if you take different distributions with the same support, let's assume that you know that the random variable is distributed between -1 and +1. Now there are infinitely many distributions which are supported within -1 to +1. And each of those is going to have a different sub-Gaussian constant or the variance factor, right? But then if the only information you have is that the random variable is bounded between -1 and +1, then the best that you can do is use a variance factor of 1, right? You can't do anything better than that. But if you know the actual distribution in question, then you can get even tighter bounds. So if you know the actual distribution, then the best thing to do would be to use the Chernoff bound, right? That is optimal. But in many problems, we don't know what the actual distribution is. So for example, when we took the Johnson-Lindenstrauss lemma, when we proved this, we used the property that the random variables in question were Gaussian, or when you look at x square, it's chi-square distribution. And using that, we could derive a tail bound. But now if let's say I change this particular distribution to something else, then obviously we may or may not be able to derive a tail bound. And this ultimately depends on how well you know the random variables in question. Okay. So henceforth we will try to generalize these results. What if I have a function of general random variables? What can I do? What properties do I need on that function in order to still be able to obtain an exponential tail bound? Right? So if you want an exponential tail bound, then these techniques would work. But in certain applications, you can't even derive an exponential tail bound, in which cases you typically use something like a Chebyshev inequality or a Markov inequality. Okay. So in the previous class, we saw some properties of sub-exponential random variables, and in this class, we'll explore a few more properties before trying to look at more general problems. Right? What if the function in question? What if I have n random variables, but I want a tail bound not on the sum, but instead some complicated function? Then what can I do? Is it still possible to derive an exponential tail bound? What are the properties on this particular function to still be able to obtain an exponential tail bound? Okay. So we've seen various equivalent definitions of sub-exponential random variables. Right? And one property that we saw, or characterization of sub-exponential random variables, was that the moment generating function, expected value of e raised to lambda x, is less than or equal to e raised to lambda square k phi square for lambda being essentially between minus 1 by k6 and plus 1 by k6, or absolute value of lambda being less than or equal to 1 over k6. Okay. Now, if we know this, then let's see what is the best tail bound we can derive, right? So, essentially, let's try to find a bound on the Chernoff exponent. So, what can I say about, so psi x of lambda is less than or equal to lambda square k phi square for lambda in this particular range. So, what can I say about psi x star of t for any t greater than or equal to 0? This is going to be greater than or equal to what? Yes? Well, it's greater than or equal to 0 for sure, but then we know what I've given you psi x of lambda, so what would psi x star of lambda be? Just give the expression. Okay, we have to do some form of optimization, but even before optimization, let's set up the optimization problem. Are you sure it's lambda square k phi square minus lambda t? Correct. It's lambda t minus lambda square k phi square, right? So it's fine, lambda t minus lambda square k phi square, and then okay, supremum. What is the supremum taken over? Lambda. So lambda should be greater than or equal to 0, but is that it? Right. So all I know is that psi x of lambda is less than or equal to this only for absolute value of lambda less than or equal to 1 over k6. Right? So it has to be less than or equal to 1 over k6. Right? So it's a constrained optimization problem. Okay, so what will this be equal to?
These functions depend on all lambda greater than 0.
Which one?
Like in general.
So in general, let me put this down. So psi x star of lambda is greater or it's equal to the supremum over all lambda greater than or equal to 0 of lambda t minus psi x of lambda.
There can be some lambda which is greater than 1 by k6.
Correct.
This can be more tighter.
True, it could be, but I don't know what psi x of lambda is for lambda greater than 1 over k6, right?
Now we are only seeing that.
Correct. I'm giving you a bound on this particular log moment generating function only in a certain range. Outside that, I'm not telling you what it is. Right? And that's the reason why I cannot take the supremum over all possible lambda greater than 0. Because I know the function value only in that particular interval. Right? Okay. So how do we maximize this? Now remember, this is a function of both lambda and t. well, I could just take the partial derivative and set it equal to 0 and find out where the stationary points lie. What does this give me? Yeah? Okay, so t minus 2 lambda k phi square equals 0, or whatever lambda, or the lambda star is equal to t by 2 k phi square. Oops. Correct? Okay, but is this true for all lambda? As long as if t by 2 k phi square is less than or equal to, I think it is 1 over k6, correct? Or t is less than or equal to 2 k phi square by k6. Okay, so now what do I do if t is greater than 2 k phi square by k6? Lambda star will be 1 by k6. And why is that? Because it is?
Subliminal will lie ahead of that, it will be increasing in that way.
It's an increasing function. Correct. If t is greater than 1 by k6, sorry, t is greater than k phi square by k6. Okay, now what if I plug these back into psi x star of lambda? So psi x star of t. So it is greater than or equal to t square by 4 k phi square if so t is less than or equal to 2 k phi square by k6. T by k6 minus k phi square by k6 square. Correct? So what does the tail bound look like? Now this of course only gives you the right tail, right? But then it turns out that the left tail will be essentially symmetric. Right, so probability absolute value of x greater than t is less than or equal to 2 times e raised to minus t square by 4 k phi square if t is less than or equal to 2 k phi square by k6 and it is less than or equal to 2 times e raised to k5 square by k6 square, which is essentially a constant, times e raised to minus t by k6 if t is greater than 2k5 square by k6. Right? In fact, it is less than or equal to this for all value of t greater than 0. Right? Because lambda square, it's equal, so the lambda which achieves the maximum is equal to t by 2k5 square if t by 2k5 square is less than or equal to this. But then it's always, I can always plug in 1 over k6 and it's still going to give me an upper bound on the t. Right? So in fact, this bound is true for all t greater than or equal to 0. But then if t is less than or equal to 2k5 square by k6, then this is a better bound. Right? So in fact, the probability that the absolute value of x is greater than t is less than or equal to the minimum. Okay, let me put it that particular way. So it is definitely going to be less than or equal to this, but if t is less than or equal to 2k5 square by k6, then it's also less than or equal to this. So this says that in a certain regime of t, the absolute value of x has a sub-Gaussian tail. Right? If t is not too large, then this tail bound decays much faster than e to the minus t. But for large t, it basically has an exponential tail. So this is what is called, sometimes called the small deviations regime. So in the so-called small deviation regime, you have a sub-Gaussian tail. But essentially the large deviations regime, that is for large t, you have exponentially decaying tails. Right, any questions? Okay, so now let's suppose that I have a bunch of random variables, all of them being sub-exponential. What can I say about the sum of those sub-exponential random variables? So suppose x1, x2 up to xn are independent, and xi is basically sub-exponential with parameters k5 I and k6 I. Right? So basically e raised to expectation of e raised to lambda xi is less than or equal to e raised to lambda square k5 I square for absolute value of lambda less than or equal to 1 over k6i. Then is it true that the sum of these random variables is also sub-exponential? And if so, what are the parameters? So what can I say about this? Correct. So firstly, okay, let's just do this step by step. So it is e expected value of e raised to lambda summation I equal to 1 to n xi, right? But I'm telling you that all the xi's are independent. So e raised to lambda times summation xi is e raised to product of all I equal to 1 to n e raised to lambda xi, right? The random variables are not necessarily identically distributed. They're independent but not necessarily identically distributed. So this is equal to the product of the expectations. But then I have a bound on the product of expectations. So this is less than or equal to e raised to product I equal to 1 to n e raised to lambda square k phi I square. But for what values of lambda is this valid? Correct. So remember that each bound is valid only in a certain interval, and for all of these bounds to hold, it should be valid in the intersection of all of these intervals, right? So basically absolute value of lambda should be less than or equal to 1 over k6i for all I, right? Or in other words, absolute value of lambda should be less than or equal to the minimum over all I of 1 over k6i, right? Okay, but this is simply e raised to lambda square summation I equal to 1 to n k phi I square. So x, the sum, is also sub-exponential, but with a different set of parameters. And what are the parameters? It is, well, if I say that xi is sub-exponential with parameters k phi I and k6i, then the sum is going to be sub-exponential with parameters square root I equal to 1 to n k phi I square and the maximum over all possible I k6. So this means that if I look at the probability of summation I equal to 1 to n xi, what's the probability that this is greater than t? This is going to be less than or equal to 2 times expected value of minus t square by summation I equal to 1 to n k phi I square if t is less than or equal to 2 times summation of I k phi I square by the max overall I of k6, and it is less than or equal to 2 times expectation of whatever k phi. K phi I square divided by the max over I k6 I square minus t by max over I k6. So this is a useful bound on the sum of any general subexponential random variables. Now we'll be deriving a bunch of tail bounds, but really in most applications, knowing how to use the tail bound is more important than knowing which tail bound to use. Right? You should be able to somehow reduce your problem into deriving a tail bound of a random variable of either a sum or a function of some sets of random variables. Okay, so maybe let's see a quick application in information theory. Right? So how many of you have taken a course on information theory? Or how many of you have not taken a course on information theory? Okay, so 3 of you, 4 of you. Okay, so we'll see. Again, I'll set up one of the most simplest problems that we can think of, and that is the source coding problem. All right. Now, the source coding problem, simply stated, is the following. I give you a sequence xn, which is just a vector x1 up to xn, with each xi being IID distributed according to some known distribution px. Okay, it's a discrete random variable. Each xi is a discrete random variable which is independent and identically distributed according to some known px. The goal is to basically compress this or encode this to a binary vector of length nr. So this is a vector c1 up to cnr, with the guarantee that you are able to recover xn with high probability. Okay, so it's a standard compression problem. I give you a sequence of length n, right? If I were to just naively store xn, remember, it's a discrete random variable. Then how many bits would I need? No, it's an arbitrary vector xn, and I don't give you any other information. What is the number of bits that you would need? Yeah. Okay, let's forget about entropy for now. Something much simpler. You have to naively just store xn in binary. Yeah. Yeah. So it basically would be n times log of the cardinality of x to base 2. Right? Each symbol is just stored in binary representation. So you just basically list all the values that x can take in binary format. I just represent each xi in the binary format. For example, if all of these are, let's say, 8-bit ASCII characters, then storing each xi takes 8 bits. Correct? And using 8 bits, there are 256, 2 to the 8 possible values, 256 possible values. So the alphabet size is 256. So basically you need R being log size, the seal of log size of x. Okay, so is it okay so far? Fine. The question is, now if I tell you that xn is drawn according to a certain distribution, can I bring down R? Is it possible to use fewer number of bits to store this particular sequence xn? Okay, but all I want is only an approximate recovery guarantee. It's okay if I'm not able to recover the entire sequence xn all the time, but maybe for almost all xn I should be able to recover it. But for certain, with a tiny probability, it's okay to go wrong. So basically we want R to be small, basically as small as possible, and I will tolerate a small probability of error. Let's say less than or equal to 2 to the minus 0.0001 times n. So I want this probability of error to be exponentially decaying in n, but it could be a small exponent. I'm not worried about how large the exponent should be. Okay, is the problem formulation clear? The goal is to design these functions, encoder and decoder, such that R is as small as possible. R is fixed for a given px, and the probability of error is as small as possible. Let's say exponentially decaying in n. Okay, so no questions? Alright, and I don't care about anything else. I allow as much computation you have the freedom to choose as complex an encoder and as complex a decoder as you want. Okay, so what do you think I could do? Yeah, quantization won't work. Quantization is something different, right?
Find the inputs that occur most probably.
Okay, yeah,
And just encode them.
Correct.
Without
correct. So one thing to do is to sort of, you list all the sequences in decreasing order of probability, and then choose the top certain number of sequences. And you choose as many sequences as possible as long as the probability of error is sort of small, it's not too large. Right? And then you try to find out what is the number of sequences you can encode. You list all of those sequences and store them using NR bits. Okay. But let's look at a slightly simpler scheme. Alright, so I'll define this T epsilon as a set, as the following set. So it is a set of all sequences xn such that if I look at the frequency of occurrence of each symbol in Xn, it is close to the true probability value. So let NA of Xn basically be number of times the symbol A occurs in Xn. So for example, if I have a sequence like alpha, beta, alpha, 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 gamma, delta, if this is one particular sequence, then what is n alpha of Xn? It's 4, right? N beta of Xn. So if this is my Xn, let me take this. So I just count the number of times symbol alpha occurs. This is just 4. In beta Xn is 1 because beta occurs only once. In gamma Xn equals 2, and n delta Xn equal to 1. I just count the number of times each symbol occurs. And I'll define this set, which is parameterized by a small number epsilon, as the set of all sequences for which the number of times that particular symbol occurs, for which every particular symbol occurs, is close to the probability of occurrence. So let's take this to be n times px of A times 1 plus epsilon, and it's greater than n times px of A into 1 minus epsilon. Okay, so it's a set of all sequences for which the number of times a particular symbol occurs is close to the true probability. Now, naively, what would you expect? This the probability that a random sequence falls in this particular set. Would it be high or would it be low? Okay, so maybe let's look at a simpler case where Xn is binary. Okay, Xn can take only two values, 0 and 1. So it takes 0 with probability 1 minus p, 1 with probability p. What is this set basically? It's a set of all possible binary sequences for which the number of zeros is close to 1 minus p. It's within an epsilon of 1 minus p, and the number of ones is basically close, or the fraction of ones is basically close to p. It's within an epsilon of p. Correct? So now if I had three symbols 0, 1, 2, then this is the set for which the set of all possible sequences for which the fraction of zeros is close to p of 0, the fraction of ones is close to p of 1, and the fraction of twos is close to p of 2. Correct? That's all this set is. So if I pick a random sequence drawn according to px, what would you expect the fraction of zeros, fraction of ones, fraction of twos, fraction of threes to be? They should be close to their corresponding probabilities. So intuitively, you would expect this set to have high probability. Correct? So now my scheme for compression would be the following. So I give you the following compression scheme. Right? So the compression scheme is the following. I list down all possible sequences in this set T epsilon. Okay? And for each of these, I assign a unique binary string. How many binary strings do I need to assign? Or how many bits do I need to represent all the strings in this particular set? Correct. So log base 2. So list all sequences in this set T epsilon. The number of sequences is basically the size of this particular set. So I can do this. So I list all of this in binary. Right? Or basically I assign an index. So list all of these sequences and assign a binary string or index to each sequence. Right. In order to do this, I need log size of T epsilon many bits. Correct? Do you agree? So what can you say about the rate of this? Okay, and the compression scheme is the following. The encoder, so given this particular input, it basically looks within T epsilon to see if this particular sequence is present or not. So if the input sequence is in T epsilon, it basically outputs the index. Okay. And if not, it doesn't matter, you just output the all zero sequence. Say. Okay. And the decoder does the following. So basically it knows this set. This set is known to both the encoder and the decoder. So while decompression, you just look at this particular T epsilon. There's some valid index which is fed as the input to the decoder, and it just outputs that particular sequence. Okay, is this scheme clear? It's not a particularly efficient scheme, but some scheme, right? Okay. So in this case, what would the rate be equal to? The rate of this particular scheme? It's basically the number of bits that you need to represent the compressed sequence. What would that be? Yeah? Correct. So it's log T epsilon, right? It's log T epsilon by n. So nr is equal to whatever C log of T epsilon. And what is the probability of error? Yeah. So when does an error occur? when the sequence is not in this set T epsilon. So if the sequence were in T epsilon, then you would basically be outputting the correct index, and the decoder would output that sequence back. If that sequence were not present in T epsilon, then the encoder outputs the all zero sequence, and the decoder outputs the sequence corresponding to the all zero sequence. So it's wrong, right? So you make a mistake if xn is not in T epsilon. So this is basically the probability that xn is not in T epsilon. So what is the basically what can you say about this particular probability? How do we analyze this probability? Correct. So if it were binary, then it basically is what the probability that the number of zeros is not, the number of ones is not close to NP. And for that we already have a tail bomb, right? But now what I want is, it's not just zeros, I have to correct zeros, ones, twos, and so on for all symbols. How do we analyze this? Yeah. Okay, so let's maybe write this down. So the probability that xn is not in T epsilon is basically equal to the probability that for at least one symbol, the number of symbols that appear in xn is not close to the true probability. Right? So NA of xn is either too large, so it's greater than n px of a times 1 plus epsilon, or NA of xn is less than n px of a into 1 minus epsilon for some symbol a. Right? But then what kind of a variable is NA of xn? So it's the number of times a particular symbol A occurs in xn. You are counting the number of times, let's say 0 occurs in xn. Right? So the number of times is basically binomial, or you can write in terms of, can you write it as a sum of random variables? Yeah? It's a sum of basically Bernoulli random variables, right? And we have a tail bound for this. But then how do I represent it as a sum? What would I need to do next? So this happens for some a in x. We know that for any a, probability that NA of xn is greater than n times px of A into 1 plus epsilon, or it's less than n times px of A into 1 minus epsilon. This is exponentially decaying in epsilon square n. Some constant times epsilon square times n. It's just the sum of Bernoulli random variables. Right? This is for one particular A. But we're saying that the probability that xn is not in T epsilon is the probability that this does not happen for some A. So what's the natural step? Correct. We just use the union bound. Right? So this is the probability that xn is not in T epsilon is less than or equal to summation. So this is basically a union of events, each event corresponding to a particular A. So this is less than or equal to summation over all A in X, probability that the number of times the symbol A occurs is greater than npx of A into 1 plus epsilon, or Na of xn is less than npx of A into 1 minus epsilon. And this is less than or equal to the size of x times 2 to the minus constant times epsilon square. Now this is basically a constant, right? So in other words, the probability of error decays exponentially. Constant prime times n epsilon square. I'm sort of skipping many steps in between, but this is just to get a flavor of how you would use these tail bounds in a particular application. Typically, whenever you're analyzing probabilities of error, the standard tools that you use are always the same. You use a union bound at some particular point. You try to write the bad event as a union of multiple events, and where each event can be bounded using some kind of a concentration inequality. Okay, so let's stop here.